In the first part of our section on series, you have to learn 5 different convergence tests, 5 different ways to test whether or not a series converges or diverges. You've learned one already, that's the nth term test, the divergence test, but that's only a rule out test. It cannot prove that a series converges. So today you learn your second test, and that will be a test which shows whether a particular type of series converges or diverges. So it'll show you one or the other, converges or diverges, but you'll learn about a particular family of series, how to identify them, and how to test whether they converge or diverge. Before we start that, keep this in mind as sort of the big picture for this first half of the series section. We have 2 big questions. I'll present you with a series, and you ask these 2 questions. Does it blank? And if it converges, can we calculate its blank? So pause, fill in the blanks. Of course, this is, does it converge? Because if it doesn't converge, if it diverges, then the series is useless. We have absolutely no use for it. So this is very important in real mathematics. If it does converge, then can we calculate its sum? And I put sum in quotation marks because that's not a true sum. That's defined the way we defined it in the previous video. So those are our 2 big questions. Now, this second one here, can we calculate its sum? The answer to that is usually no. We cannot. For most series you run into, you cannot calculate some sort of sum. For example, the series used to calculate pi, for example, or e, those are non-terminating, non-repeating decimals. They don't have a fixed sum. There's no limit to what those partial sums approach. That's true most of the time. It's the rare exception where you can calculate the sum. And today we look at a family of series that fits that rare exception where you can calculate the sum. And that family is called the family of geometric series. So here are 4 examples so you can kind of see the pattern. You may want to pause the video, spend some time looking at these, and I strongly suggest you write them down on a piece of paper because we're going to come back to them again on subsequent boards. Okay, take a look at these. Each of these is a geometric series. You see what they have in common, what makes them all geometric. You may not see that right away, but it'll come out as we do the video. All right, here's the definition. What makes a series fall into this family, the geometric series? What's the form of this series that all 4 of these have in common? Well, it's this. There's some kind of root value, a base, raised to the letter n, and the series as a whole may be multiplied by a constant. Look at this one here. Compare this to this. You may be able to spot what the constant is in this one. Okay? So here's what that would look like if you wrote out the terms of the series. Notice the a is the same for all of them, so you can factor it out and put it out front of the sigma sign. Most books don't do that. They put it in here, but I think that's misleading. I think it's better to think of this as a thing, and that thing is being multiplied by a. That's much easier. A and r are constants. If you look at this first one here, you can figure out very quickly what the a and the r are. Forget the a, just look at r. What would be the base? What's being raised to the first, raised to the 0, raised to the 1, raised to the 2, raised to the 3, and you'll see what they are, and you'll also see that a in this case is 1. Again, you might want to write these down because we're going to come back to them. Okay, so geometric is a bad name for this series. There's nothing geometric about it having to do with geometry. There's a historical legacy why it's called geometric. It's also called, what kind of function is this? If you had like 10 to the n, what is that? If the exponent is here and this is a constant in the base, that's actually called an exponential function. And it's okay to call this an exponential series. It's really exponential, but the traditional name for it is geometric, which is a bad name. And r is the base of this exponential. All right, so go ahead, pause the video and write our 4 examples in that form. Figure out what the a is for each one and what the r is for each one. All right, for the first one, the base is 3. And the a would just be 1. And you'll see that that gives you the series for number 1. All right, for the second one, the base is 1/2. And again, the a out front would just be a 1. Okay? To make it quicker, I'm just going to write that. Okay? For the third one does have a non-1 value of a. Now you might say, well, how do I figure out what's what in this one? There's a trick here that will come in handy on the homework and that I'll probably put into a notes packet that I put in the topics. And that's that to figure out the value of the base, to figure out the r, what you simply do is divide successive terms. So pick any two terms next to each other and divide the second one by the first one. 3 divided by 1 is 3. 9 divided by 3 is 3. 27 divided by 9 is 3. If you always get the same number, it's a geometric series and that's the base. You could do that here. You see, if you divide this by that, you always get the same number. Same thing with this one. Same thing with all of them. So if you do that for number 3, you get that the base is negative 1/2. Right? That's what's being multiplied times each prior term to get the next term. But you have to put a 6 out front to get the actual series as it's written. And finally, with the last one, if you divide successive terms, you get 1/10. And you have to put 0.9 out front as the multiplier. Right? So for this one, A is 0.9, R is 1/10. Right, this is something just to know. Now we can prove it. This year we're not going to do this proof. There'll be something in topics that's completely FYI, not even a bonus question, and I'll mention that on the next board. But you just want to know this, and it's kind of common sense. Look at the 4 series on the previous page and think about whether they would cross finish line or not. How do you make each successive term shrink to 0, that kind of thing. And think to yourself, what would be the requirement on the base to keep this series from getting bigger and bigger, to keep the partial sums from exploding, to make it so that there's a finish line that you can never cross? And the answer to that is the absolute value of that base has to be less than 1. If it's bigger than 1, every time you multiply by that again and again, the terms keep getting bigger, right? But if it's smaller than 1, they'll keep getting smaller, they'll shrink to 0, and further you can prove it converges. But on this year, we're not going to do that proof. All right, and then finally, I said earlier there were 2 questions you would ask of any series. One, does it converge? And we will be able to answer that for the series we look at, all the different series that we look at. The second question was, can you calculate the sum? And I said the answer to that is usually no. Usually you cannot calculate the sum. Can't be done. But for the geometric family of series, there's an easy formula. This is the formula. There's the geometric series, the base, right? And notice I'm not writing the letter A out front because you don't need to. Whatever you get for this gives you this kernel, the sum for this kernel. And if there's an A out front, you just multiply it times that. So it's just 1 over 1 minus the base. That's it. Now this can be proven. It's an interesting proof. I've uploaded it to topics, but it would not even be a bonus question because you could just copy it right off the proof. I put it there as FYI only for someone who might want to be a math major or who likes solving puzzles. All right, let's look at our 4 examples and calculate the sum for each one. Okay, for this first one, what would R be? R would be 3. Okay, and if you went to calculate the sum, you'd get a ridiculous answer. You get something negative. Why is that? That's because this only works for converging geometric series. So only if our absolute value is less than 1. Otherwise, it gives you nonsense. It will give you a number, of course. You could plug 3 in there, but the number will be nonsense. So the first thing you have to do is check to see if the series converges. Of course, that's our first question. That's most important. Then if it does converge, you put the R in this formula and you get the sum. All right, so this diverges. So we cannot calculate the sum for it. Now look at 2. In fact, why don't you go through and do all 3 and then pause the video and calculate the sum for the other 3. This one, the base is less than 1, therefore it converges. So we do 1 over 1 minus 1/2, right? And we get, of course, 2. And this is actually the series that was in the lab that you did. All right, take a look at this one. Now it may seem a little strange that that's a negative 1/2 and the series alternates, but this formula still works. And if you go through and do the calculation, you get 4. 1 over 1 minus negative 1/2, figure that out, and then multiply that times 6, right? The sum formula I've put up here gives you this value as a number, and you multiply it times 6, and you get 4. And finally, for this last one, r equals 1/10, a equals 0.9. So put the 1/10 in here, figure it out, multiply it by 0.9, and you get the expected sum of 1.